There are many different kinds of devices or gauges, often referred to as a barometer, that can be used to measure pressure. One of the simplest pressure gauges is the mercury barometer that is used to measure atmospheric pressure. It consists of a tube sealed at one end, filled completely with mercury, and then inverted so that the open end is under a surface of a pool of mercury. The space above the mercury at the top of the tube is empty, except for a small amount of mercury vapor, so that the pressure here P1 is essentially zero. The pressure P2 at point A, at the bottom of the mercury column, is the same as the pressure at point B, namely atmospheric pressure, because these 2 points are at the same level. With P1 equals 0 and P2 equals P atmosphere, it follows from equation 11.4 that P atmosphere equals 0 plus rho gh. Thus, the atmospheric pressure can be determined from the height h of the mercury in the tube, its density, and the acceleration due to gravity. Depending on a person's altitude near the surface of the Earth and the local weather conditions, the atmospheric pressure can change. The lower the atmospheric pressure, the shorter the height of the column of mercury in the tube. Usually, weather forecasters will report the pressure in terms of the height h, expressing it in millimeters or inches of mercury. For instance, using P atmosphere equals 1.013 times 10 to the 5th pascals, and rho equals 13.6 times 10 to the 3 kilograms per cubic meter for the density of mercury, we find the height h equals 760 millimeters, or 29.9 inches. Poor weather conditions are associated with low-pressure systems. Hurricane Wilma, for example, which made landfall in western Florida in 2005, was at the time the most intense tropical cyclone in the Western Hemisphere. Its lowest pressure was measured at 25.69 inches of mercury. Another common type of pressure gauge is an open-tube manometer, which consists of a U-shaped tube with one end open to atmosphere. The tube contains a liquid, which again is often mercury, and the other side is connected to a container at a pressure P2 that is being measured. When the pressure in the container is equal to atmospheric pressure, the liquid levels in both sides of the tube will be equal. When the pressure in the container is greater than atmospheric pressure, as shown in the figure, the liquid in the tube is pushed downward on the left side and upward on the right side. The relation P2 equals P1 plus rho gh can then be used to determine the pressure in the container. Atmospheric pressure exists at the top of the right column so that P1 equals P atmosphere. The pressure P2 is the same at points A and B so that P2 equals P atmosphere plus rho gh, or P2 minus P atmosphere is equal to rho gh. The height h is proportional to the change in pressure, which is called the gauge pressure. The gauge pressure is the amount by which the container pressure differs from atmospheric pressure. The actual value for P2 is called the absolute pressure. From a problem-solving standpoint, it's important to make the distinction between gauge and atmospheric pressure. For example, in problems involving a container of liquid open at the top to air, the pressure at the bottom will be the absolute pressure, which is rho gh plus 1 atmosphere.